Hello, everyone. Welcome back to Calculus. So I think that this would be the very last official class video that I'm making, but we do have a few class sessions after this one in which you guys will be able to ask questions. We'll be able to just have a good review of everything we have learned over this exciting class that we've all had together. I think that we're going to be spending a fair amount of time maybe going over some of the AP exams just to test our mastery of all of these concepts we've learned all the way from the beginning when we learned limits all the way up to this point where we are covering infinite series. So there might be one more lesson after this. I don't know. It depends on how far we get today. But this could possibly be the last official class before we start our review of everything. So we want to start just by reminding ourselves what an infinite series is. So an infinite series is what we get when we add together a finite number of terms. No, not finite. Sorry, I meant to say an infinite number of terms. And remember, in the last class, we remember thinking it just doesn't make much sense to add together an infinite number of things. And in some cases, that's correct. In other cases, it's not quite accurate. We can add together the infinite number of terms in a sequence like this in an infinite series, if and only if the series converges. So if it converges, we can definitely add them all together. If it diverges, we have no luck. So it kind of like what we did with improper integrals, we have our own methods of determining whether an infinite series converges or if it diverges. And it is a really extremely useful tool to have at our disposal because we can tell right away if we're able to take the series or not, if we're able to add together all of the terms in an infinite series, only if it converges. And it's just a really nice strategy to have on hand. So we have this one right here. We want to first determine, well, actually, I don't think we're going to add this together. We just want to get a yes or no answer to see if this converges or not. So let's remind ourselves what convergence means of a geometric series. So that's where we left off in our last class. We covered the convergence and divergence of a geometric series. So we want to see if this looks like a geometric series. Because if it does, we have some very straightforward rules we can use to determine if a geometric series converges or if it diverges. So let's see if we can maybe rewrite this in such a way so that it does kind of look like a geometric series. So remember that in general, a geometric series looks something kind of like this, where we have sigma, the sum going from n is 1 to infinity. And it would be something kind of like this. It would be a times r to the n minus 1. And then that would get us a plus a times r plus a times r squared, and then it would just keep going on and on and on. So remember, as a review from last class, if we're able to definitively prove that this series converges, we can find the sum. And if it does not converge, we have no hope of finding the sum. It'll just keep increasing, increasing on and on and over again without bound. So we can only add together the terms of an infinite series if it converges. So let's see if we can determine if this is a geometric series or not, and if it is, how we can test it for convergence. So at first glance, it doesn't really look like an infinite series. It doesn't look like the thing that we had a few seconds ago on the screen, but looks can be deceiving. I think we want to clean this up a little bit and maybe rewrite it in a certain way so that it definitely does look like more of a geometric series. We just have to rewrite it using some of our algebra rules and see if we can make this look like a geometric series. So one thing we might want to do would be to use our laws of exponents and write this as 2 squared and then that thing to the nth power. So that's like saying we just have 4 to the nth power if we expand that. So this would be 4 to the n. And then what I want to do is, I think this is going to end up being some kind of a fraction. So what I want to do is I want to take this 1 minus n, and I want to rewrite that using laws of exponents. So what I want to do is here, I think I'll just scribble it off to the side real quick so we have a clear idea of what I'm trying to do. So we have 3 to the 1 minus n. I want to convert that into a fraction. And remember that we can't just willy-nilly convert things into fractions arbitrarily. We have to make sure that things kind of balance out. Kind of like in algebra, whenever we're trying to solve for a variable, we have to add one thing to the one side, and then we have to add the same thing to the other side in order to keep things balanced. So what I mean by that is if we want to convert this into negative, if we want to make the exponent negative, we're going to have to do something to counteract that behavior. We're going to have to do something to counteract the thing becoming negative. So what I think we should do is we should take this 3 over 1, take the reciprocal, so we get 1 over 3, And then having done that, we can make this exponent negative. We're going to have negative 1 minus n. And then let's see if we can clean this up even further. So instead of negative 1 minus n, let's distribute the negative. So we're going to have a positive n. We're going to have a negative 1. So altogether, we're going to have 1/3 to positive n minus 1. So this is our new exponent. So let's just go ahead and write this as 1/3 to the n minus 1. So let's go ahead and substitute that in for the 3 to the 1 minus n. So I'm going to write this on the bottom. We're going to replace the 3 to the 1 minus n power with a 1/3 to the n minus 1. Sum of n equals 1 up to infinity. So this thing is already starting to look more like what we're used to seeing. But one thing we have to do first is make sure they have the same exponent. So notice how upstairs we have an exponent value of n, and then notice how downstairs we have an exponent value of n minus 1. So we have to do some kind of manipulation to make sure that the exponents are the same. We either want them both to be n or we want them to both be n minus 1. So recall that the general form of a geometric series is something kind of like this. We always want it to be in terms of n minus 1. We always want n minus 1 to be the exponent. So that means we can leave what we have downstairs alone. The only thing we want to do now is to change our numerator. We want to change the numerator so that we have not a 4 to the n power, but something to the n minus 1 power. So let's remind ourselves how that could be possible, how we could possibly do that. So I want to write this off to the side again. So if we have 4 to the n power, let's see what kind of a manipulation we can do to change this, change the exponent so that it's n minus 1 upstairs. So what we could do is we could write this as 4 to the first power times 4 to the n minus 1. And you might be wondering, why does this work? Does it work? Let's just verify that this works. So there is a special rule of exponents that tells us that whenever we have a to some power and then times a to some other power, it could be any number. Whenever we have a situation like this, we always add the exponents together. So this can be written as a to the x plus y. And then this is kind of similar to, instead of starting with this one and moving our way to the right, we're actually going to be starting with 4 to the n, and we're going to be breaking it up into 2 separate n values. So we're doing the reverse of what we have written here above with the a's. So let's see if our math checks out here. So if we have 4 to some power times 4 to another power, there is that rule of exponents that tells us that whenever we have a situation like this, we can write that as the single base applied to the power of the sum of the exponents. So it's going to be applied to the power of n minus 1 plus 1. We can see that the negative 1 cancels with the positive 1, and things work out really, really nicely. We do, in fact, end up with what we started with, so we know we did it right. We know that it's perfectly legal and valid to do what we've just done here. But why do we want to do that, though? Let's remind ourselves what the point of this even is. Why did we even do this manipulation? I am so glad you asked. So let's go ahead and take this part and rewrite it, replace this with what we just found to be equivalent to it. And I'll show you why it's significant. So instead of 4 to the n power, I'm going to just do it on a new line. We're going to have 4 to the first power times 4 to the n minus 1 power, all divided by 3 to the n minus 1. Sum starting with n is 1, going all the way up to infinity. So it works out really nicely. The reason why we even did this derivation is that we have the same exponent power upstairs that we have downstairs. We have an n minus 1 upstairs, we have an n minus 1 downstairs. Hey, life's good. That's exactly what we want. So remember, we set out to prove that this thing converges or diverges. We have to prove either one of those things. It's going to be one or the other. And remember that we had to first determine if it really is a geometric sequence. Or sorry, I keep saying sequence when I mean series. We have to prove if it's a geometric series before we can use our specialized tools for determining geometric series convergence. So that's where we are. That's what step we're on in the process right now. We're just trying to verify that this is a geometric series. We want to verify that it's written like a geometric series so that we can use the geometric series rules for convergence and get our answer. So we can take this 4 right here, and this is a special rule that applies to series. It applies to series, just like it applies to integrals, just like it applies to limits and derivatives. Remember that if we have something like this, maybe the integral of 2x squared dx, remember that we can always move a constant out front. Same thing applies to derivatives. And then the same thing also applies to limits. We can always move constants to the front of the outside of the operator without changing our answer at all. So let's go ahead and do that. Let's move this 4 to the outside. We're going to make this 4 times the series. This is going to go away. And then the whole point of that is because now we can write it in this form. We have 4 times the infinite series, starting from 1 going to infinity, of 4 over 3. So it's really nice having 2 things with the same exponent because we can just write them as a single fraction to a single power. And it works really, really nicely. So now we absolutely do have an infinite, we do definitely have a geometric series. So we want to identify A and we want to identify R. So remember, in an infinite series, A is always going to be the very first term in the sequence. And then R is always going to be the common difference. So for example, if we have something like this, we have, here, I want to just write it like this. What if we have 2 plus 4 plus 8 plus 16 plus 24? And by the way, this is not related to the series we're working on right now. This is completely separate from all of this stuff. I'm just using this as kind of a review so we can remind ourselves what A really means and what R really means in the context of a real series. So A is always going to be our very first term, our very first element in the set. So A would be 2. And then R is always the common difference. That would be the number you have to multiply one number by to get to the next. So 2 times what number is 4? 2 times 2 is 4. And then 4 times 2 is 8. 8 times 2 is 16. And then, oh, sorry, I made a mistake there. How embarrassing. Really sorry about that. I'm glad I caught that. So the common difference still applies. 8 times 2 is 16. 16 times 2 is 32. And then we go to 64 and so on and so forth. So everything we get is, every number we get is the product of 2 in the previous element. So R, the common difference, is 2. So that's what A and R mean in the context of an infinite series, infinite geometric series. We can see that in this case, A is going to have to be 4. And the reason A is going to be 4 is because if we plug in a 1 right here for n, we're going to have 1 minus 1, which is 0. The whole thing just becomes 0. And then 4/3, or anything in parentheses, doesn't matter what we have in parentheses, anything to the 0 power is going to be 1. So that means our very first element, A, is going to be 4 times 4/3 to the 0 power, which is just 4 times 1, which is just 4. So we can tell that the value of A in this geometric series is 4. Now let's see if we can identify R. So R is going to be the thing that we raise to the exponent power. So in this case, we can see that R is going to be 4 over 3. That is our common difference. 4/3 is R. And remember, in the last class, we talked about a special rule that helps us determine convergence or divergence of a geometric infinite series. It tells us that if the absolute value of R is less than 1, then the series converges. So let's apply that rule to our series, what we have right now, and then see if this converges. So the value we have for R is 4/3. Absolute value of 4/3 is still going to be 4/3. We want to see if this applies. So we see that 4/3 is greater than 1. So this does not apply. This is false. So this series actually diverges, and we cannot find the sum of a series that diverges. So that's all we can do right now. The only thing we can do with this is to prove that it diverges. We can't find the sum, can't do anything else with this one. This infinite geometric series diverges. So it's really good to have practice in looking at something like this and then seeing if there's a way to write it as a geometric series, because at first it does not look like it at all. But we've seen just now that we can take something like this, use some algebra tricks, and convert this into something that does look more like a geometric series. Something that we can definitely prove converges or diverges. So that's it for that one. Do some more examples here so we have a really good understanding of this topic. So let's talk about a harmonic series. This is going to be a new type of series. What is a harmonic series? A harmonic series looks like this. It's going to be the sum of n equals 1 to infinity of 1 divided by n. This is a harmonic series. So let's do a partial sum. Remember that a partial sum is just going to add together a finite number of elements. In a geometric series, we add together everything from 1 to infinity, but in a partial sum, we stop at an endpoint. We're not going to go to infinity. So a partial sum can be as big or as little as you want. I think we should do maybe 4 or 5 terms. So let's see what happens when n is 1. This is going to become 1. We're going to have 1 over 1. So our first term is going to be 1. And then we're going to move on to n is 2. So whenever n is 2, our next term is going to be 1/2. And then after that, we have n is going to be 3. So we have 1 over n, 1/3. And then we have n is equal to 4. So we have 1 over 4. And then let's just do one more. 1/5 would be our very last term. So I just did a partial sum of this harmonic series. I just found the first 5 elements in the set, or the first 5 terms of the harmonic series. So let's see if we can prove definitively if this thing converges or not. So let's see here. So we have, let's just see what happens if we add together maybe the first few terms. Let's start maybe with a partial sum of just 2 terms. So we'll have, maybe we'll just start with s of 1. So s of 1 would be the first element. S of 2 would be the partial sum with only 2 elements. 1 plus 1/2. And then we have the partial sum with 3 elements. We have 1 plus 1/2 plus 1/3. And if we do the fourth partial sum, we have 1 plus 1/2 plus 1/3 plus 1/4. So we want to compare this partial sum with something that's really, really similar to it. We want to compare this partial sum to the following, to 1 plus 1/2 plus, not 1/3 plus 1/4, but plus 1/4 plus 1/4. We're going to have 1/4 occurring twice in this partial sum. So what we have over here to the right side of the inequality operator, this would be 1/2 plus 1/2 plus 1. So 1/2 plus 1/2 is 1, and then we're going to have 2 over here. So we can see that our partial sum that we have on the left side of the inequality operator is greater than 2. And you might be wondering why this is important. We'll see in just a few minutes why it's important to know that this is greater than 2. So let's skip a few. Let's, instead of going to s sub 5, let's jump down to s sub 8, the 8th element of the partial sum. So we would have 1 plus 1/2 plus, skip a few, plus 1/7 plus 1/8. And then from there, we can compare this with some different things. But you know what? I think I do actually want to expand this and write all of them in there. One-fifth, 1/6, and yeah, I think that's all of them. That's all we really need for the 8th partial sum. So we want to do something similar to what we did in the last example. I want to replace this with 1/4 plus 1/4, And the reason we want to do that is because we know that this part would be 2. So this part's actually going to be greater than 2. And then we have, give me a quick second. I think I need a little bit more room to write. And then what I want to do after that is write this 1/5 plus 1/6 plus 1/7 plus 1/8. I want to replace all of those with 1/8. And then we know, I think it's going to be greater than, but we'll also test that. So we want to do what we did before with the fourth partial sum. We're going to make this into a 1/4 plus 1/4, which means this first part, I want to color code it a little bit. So this first part in blue is greater than 2. We know that from the fourth partial sum we just did. And then we want to do the same, something similar with this part right here. So I want to replace it with 1/8 plus 1/8 plus 1/8 plus 1/8. So this is 4/8, which is just another fancy way of saying 1/2. So this is just going to be adding 1/2. So we have 2. And I want to maybe color code this part as well. So we're comparing this partial sum to this 1/2. And we can tell that it definitely has to be greater than 1/2. So this gets us 5/2. So the point of all that is to prove that this part of our partial sum, s of 8, it has a value greater than 5/2. And again, it may not be clear why we're doing this, but in a few minutes, you'll see why this is such a useful trick. Whoops, may have gone a bit overboard there. Greater than 5/2. So let's do the same thing for s sub 16. But before we continue, I want to maybe resize some of this stuff and make it easier to, make things a bit smaller and then move them around a little bit. Give us some more room to write. Whoops. I think I'll just move everything over here. So I want to do the same thing for an s sub 16, the 16th partial sum. So you might have noticed a pattern by now, a pattern that we can use if we're going from, for example, s sub 2 to s sub 4 to s sub 8, and then right now s sub 8 up to s sub 16. So we want to do something similar to what we've been doing so far. We still want to compare the first part of our partial sum with this 5/2. So we know that all of this going from 1 to 8 is greater than 5/2. So I want to just write this as 1 plus 1/2 plus skip a few up to 1/8. And we know that this part right here is greater than 5/2. So then let's do something similar, going from 1/9 all the way up to 1/16. So instead of 1 plus 1/9 plus 1/10 plus 1/11 plus 1/12 and so on and so forth, I want to replace all of those with just 1/16. How many 1/16ths are we going to have? We're going to have one that replaces 1/9. Hang on a second, let me move this over. Here, I'll rewrite it. So how many 1/16ths are we going to have? We're going to have one for 1/9, for 1/10, 1/11, 1/12, 1/13, 1/14, 1/15, and then one for 1/16 itself. So we're going to have 8 of these. 8 of our elements in the finite set are going to be replaced with 1/16. So this is going to turn into 1/2. So we already know that this part right here, starting with 1/1, ending with 1/8, that finite sum is greater than 5/2. So that means this part's going to be greater than 5/2 plus whatever this ends up being. So this 8/16 is just going to be another multiple of 1/2. So it's going to be, this whole thing is going to be greater than 5/2 plus 1/2, which is just going to be 3. So S sub 16 is greater than 3. And then I think we should maybe just do one more of these for S sub 32. So we're going to start with 1. We're going to add 1/2, 1/3, 1/4, skip a few, and then we're going to add 1/30 plus 1/31 plus 1/32. So we already know that everything starting with 1 and then going to 1/2 and then ending eventually with this 1/16 is all greater than 3. So we want to figure out what happens if we add another multiple of 1/16 for every other element past this one right here. So just like we did in the last few finite series, the last few finite sums, we want to take 1/17, 1/18, 1/19, 1/20, all the way up to 1/32, replace every single one of those with 1/16. How many do we want though? Let's figure that out. So we want we want to replace 1/17, 1/18, 1/19, 1/20, 1/21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So we're going to have 16 of these that are being replaced with 1/16, which is just a fancy way of saying this whole thing is just going to be 1. So this is going to be greater than our value right here that we know is 3, plus this new part of our series, which is just 1. So we have 4. So we know that the entire finite series has to be greater than 4. So if we stop at S sub 4, we have this is greater than 2. If we stop at S sub 8, we know it's greater than 5/2. If we stop at S sub 3, we know it's greater than 3. If we stop at S sub 32, we know it's greater than 4. Which means that if we have this, if we have an index, and we wanted to figure out this part, there is a special formula we can use. So we could say that S sub 2 to the nth power is greater than 1 plus n/2. And this is really useful because what if we wanted to find like S sub 100 and we didn't have time to just go through the pattern like we did for S sub 4 and then S sub 8 and then S sub 16 and then S sub 32. Having a recursive formula helps us tremendously if we want to compute really, really large values without iterating all the values that come before it. We can just jump directly to that one. So this is the formula we use. And let's see what happens as S sub 2 approaches infinity. So we can just approach it like a limit. So imagine we're taking the limit as S sub 2 approaches infinity. Well, then this would also approach infinity without bound. So n would get larger and larger. It would just keep getting increasingly larger without bound, which means that it does not really approach a certain value, which means that this definitely diverges. So this is the simple case of what we call a harmonic series, 1/2 plus 1 plus 1/2 plus 1/3 plus 1/4, so on and so forth. What we've just done is we have proven definitively that the harmonic series diverges. And it's a really handy tool to have in our arsenal because whenever we have something like this, kind of like with geometric series, remember we spent some time seeing if we can convert something into something that looks more like a geometric series to make it easier to test for convergence. And this is the same exact goal as we're doing right now with the harmonic series. We're trying to just create a way of just determining an infinite. We're just trying to find a way of proving definitively that a harmonic series converges or diverges. So if we have something that is able to be written like this, we can tell that it diverges without doing too much work. So that's the goal of this, to prove convergence much faster and easier, or prove divergence much faster and easier. That is the harmonic series. So let's do some more examples. Let's say we have the infinite series going from n equals 1 up to infinity. And I apologize if I sound congested. I am in the middle of a really severe allergy attack. So if I randomly go on mute, means I'm having like a sneeze attack or something like that. So just a fair warning, just a heads up. So we have the infinite series starting with n equals 1 going all the way up to infinity. We have upstairs, we have n squared, and then downstairs we have 5n to the second power plus 4. And we want to prove that this thing converges or diverges. So we can actually use a limit to help us with this one. So we want to take the limit as n approaches infinity of a sub n. And then we can see that we're going to have, I'm going to just replace a sub n with all of this because everything in this box is considered to be a sub n. So let's see what happens as n gets larger and larger and larger. So what I want to do is I want to take out the value of n squared from all three of these terms. So we have an n squared on top upstairs, and then downstairs we have another multiple of n squared. So let's go ahead and take out an n squared from the top, and then also take out an n squared from the bottom to simplify things a bit, to make it easier to compute the limit and to interpret the results of that limit in terms of convergence and divergence. So if we take out an n squared from upstairs, we're going to have just a 1 left over. If we take out a 1 from the sum we have downstairs in our fraction, we're going to have a 5 left over for the first term. And then we're taking out n squared from something that does not even have an n squared in it, which means we're going to turn this into a 4 divided by n squared. So n squared and n squared cancels out. And we're left with something that's a lot easier to work with, something that's easier to compute and much easier to interpret. Whoa, didn't mean to do that. So let's ask ourselves what happens as n tends to infinity. So n would just keep getting larger and larger and larger, which means this thing in the box, this 4 divided by n squared, this would go to 0 if we were to take increasingly larger and larger values of n. The entire value of what's inside the box would tend to 0. It would converge to 0. So this part in the box converges, but that's not really enough information, at least not yet, to tell if the entire thing converges. So let's see what happens as n gets larger and larger and larger. So this thing goes to 0, and what are we left with? We're going to be left with just 1/5. And remember that in order for it to converge, the limit has to exist, but not only does the limit have to exist, it has to equal 0. If the limit does not equal 0, then we cannot find the sum. This thing definitely diverges if it does not have a limit value of 0. So we have 1/5 and not a 0. So this series diverges. Whenever we're in a situation like this, the sum must, or the limit of the sum has to equal 0 for it to converge. Otherwise, it diverges. What else do we have? Let me find another good place in our book. So now we're going to do something called the integral test. So by this point, we have seen many, many different parallels being drawn between two topics we would have originally thought were not related at all. So when we first started doing infinite sequences in series, we didn't really see the connection between integrals and the concepts of sequences in series. We're probably thinking, why are we even learning this stuff in a calculus class? Why are we learning about sequences in series in calculus? But as we've done more and more examples, and as we've kind of gotten into improper integrals, learning these concepts of convergence and divergence, those concepts are the tools we have to help us make the connection, to draw parallels between integrals and infinite series. So without convergence and divergence, it doesn't even really seem like these are related at all. They seem like totally different concepts. Integrals are completely different from infinite series, but they're actually very, very, very similar. So let's remind ourselves what an integral does real quick, just the basics. So an integral is the limit of a Riemann sum. we're taking an infinite number of rectangles, I equals 1 to n, f of c sub I, which is just the value of a y value we get when we plug in a particular function value for x, and then times delta x. And this is what we get. We get the definite integral going from a to b. This is the limit definition of the definite integral, kind of like the same thing we had when we were first learning derivatives. Derivatives and integrals both have rigorous limit definitions. So this is just saying that if we have a curve, we're adding together an infinite number of rectangles. So we might have some pretty fat rectangles to start with. My drawing skills are abysmal, as always, so please bear with me. We're going to add together all of these rectangles. And then they're going to get smaller and smaller and smaller. So the skinnier the rectangles are, the more rectangles we cram into this region, the more and more accurate our depiction of this area is going to get. The closer it gets to the actual 100% accurate area value. And then sequences and series. Well, an infinite series is the same way. Instead of adding together a bunch of rectangles, we're adding together a bunch of finite terms. So they're both adding things together. So that's one major way how sequences and series are connected to integrals. Series and integrals both concern themselves with adding together an infinite number of things. And that's why it's so important to understand these things. And that's why it's being introduced in a calculus class. They both share that attribute of adding together an infinite number of things. So now that we have re-emphasized this connection between integrals and series, we want to use that connection to help us add more tools to our arsenal. We want to use that connection to help us understand and have a better sense of the convergence and divergence of some particular types of infinite series. So the next topic we're going to be discussing would be the integral test for convergence. And it looks something like this. So let's say that we have a function. Let's say we have f of x. F of x is a continuous positive decreasing function on the interval 1 to infinity. And let's say we have a sub n is equal to f of n. So I want to just write this real quick. Have some function f of x where it's decreasing, which means that f prime of x is going to be less than 0 on the entire interval. And we know that it is positive. So here, I want to put this part first. So it's going to be always positive, always above the x-axis. But then the derivative is always going to be less than 0 because this only works when we have a function that's decreasing. The integral test does not work for increasing functions. So what we know so far is that all the function values are positive on this particular interval, starting with 1 and then going to infinity on this interval. And then what else do we know? Let's just assign a value. Let's say that a sub n is equal to the function value evaluated when x is equal to n. So we'll say that the series, starting with 1, infinite series going from, that looks horrible. I think I'm just going to rewrite that. Being a perfectionist is tough when your handwriting is as horrible as mine is. So we're going to start with n is 1 to infinity, taking the infinite series of a sub n. So the integral test tells us that if this series is convergent, only if the improper integral here, I want to establish that this is kind of separate from the other stuff. These are the basic conditions that were given. This part below is the actual meat and potatoes that determines if this converges. So this part converges if the infinite series, if the improper integral going from 1 to infinity of f of x times dx is also convergent. So if the integral converges, the infinite series also converges. And then same thing applies to divergent. If this diverges, if the series diverges, or hang on, let's go the other way around. So if the integral diverges, the series also diverges. So the series exhibits the exact same behavior as the integral does. So it makes things a lot easier for some types of infinite series. It looks like it's just going to be a simple matter of taking an integral, taking an improper integral. And if the improper integral converges, if it equals 0, then if the limit equals 0 is what I meant to say, then the series definitely converges. So it's a really useful strategy when we have things like this and things that are pretty easy to integrate, and it helps us try to see if certain things converge a bit easier. So let's see here. So we are continuing our integral test for convergence. We're going to do an example, and I apologize about how everything just kind of wiped blank. It is due to my own technical difficulties. For some reason, it stopped recording immediately after we introduced the concept of the integral test, and I was forced to just kind of stop the video and restart it. So this is just going to pick up where we left off. We are given an infinite series. For example, we have one starting with n equals 1 all the way up to infinity. And I want to just rewrite the definition real quick. So it tells us that if we have some infinite series, it converges if the integral equivalent also converges. So this converges if the integral, the improper integral going from 1 to infinity of f of x, so I guess we'll just say f of n actually, f of n times dn. I think we're going to use n instead of x as the variable of integration, because then we know a sub n is equal to f of n. So a sub n is equal to f of n. So this is just the conventional notation. Whenever we're going from the sequence or series notation to a function notation, this is the convention for doing that. So this tells us that if the integral converges, if this improper integral going from 1 to infinity converges, we are absolutely sure that this infinite series also converges. Same thing for diverges. So if this improper integral diverges, then this infinite series is also going to diverge. So the infinite series behaves the same exact way as the improper integral does. And like I said, it's really useful to know the integral test because some of these things are pretty simple to integrate. And it just tells us right away if it converges or not. So it's a really effective tool to tell if certain things converge or if they diverge. So let's go ahead and do an example. So let's say we have the infinite series of a natural log of n divided by n. Natural log of n divided by n. So we want to determine if this infinite series converges or if it diverges. So we're going to use our integral test for this one. We are going to just take the definite improper integral. We're going to do the integral from 1 to infinity of natural log of n divided by n dn. So remember, with improper integrals, we can't even take an improper integral unless we're absolutely sure that it converges. Not only that it converges, though, it must converge to 0. If it converges to any value other than 0, there is no hope for us to be able to integrate this thing. So before we even continue, let's make sure that this function converges to 0. So in order to definitively prove that, we're going to take the limit as n approaches infinity of our function of integration, the function that we're trying to integrate right now. So for this one, we have a few different methods we can do to tell if the limit reaches 0. What we could do is we could make an XY table, take larger and larger and larger values of n, and then see what happens as n gets larger, see what effect that has on the function itself. Another way we could do that would be to look at a graph. We could open Desmos right now and then take a look at the end behavior, and the end behavior would tell us exactly if this thing converges to 0. Or another thing we could do is maybe apply L'Hopital's rule to this one. So remember that L'Hopital's rule is one of the most versatile, one of the most useful limit tools we have at our disposal. It's really a great way to tell if a rational limit like this if it converges to what we think it should converge to. So let's just do a quick refresher on what L'Hopital's rule is. So L'Hopital's rule tells us that whenever we have the limit of some rational function with a clear numerator and a clear denominator, the limit is equal to the derivative of whatever we have upstairs divided by the derivative of whatever we have downstairs. So what I want to do is I want to move things over a little bit, give us a little more breathing room. So we're going to apply L'Hopital's rule to this. So we want to ask ourselves, what is the derivative of whatever we have upstairs? What is the derivative of natural log of n? That would just be 1 over n. Nice and easy. And then we have the derivative of whatever appears downstairs. So downstairs we have n. The derivative of n with respect to itself is just going to be 1. So that means if we were to simplify this, the limit is just 1 over n. Much, much easier to figure out this limit compared to this one. And L'Hopital's rule is the tool we use to go from something fairly complex to something simple with just one variable appearing in the entire function. So what happens as we pick larger and larger and larger values of n? As n gets larger, what happens to the overall expression? Well, this would just go to 0. As n gets larger and larger and larger, this thing inside the box would eventually theoretically reach 0. If n could theoretically reach infinity, this thing would theoretically reach 0. So what does this tell us? It tells us that we are definitely able to take the improper integral. Without this being 0, we have no hope of being able to integrate this. But because we know for sure that it does converge, not only does it converge, but it converges to 0, we know for sure that we are able to take this improper integral. So let's go ahead and do that now that we know we can. So what do we want to use to integrate this? What integration methods are going to be helpful to us? So it's always a really good idea to see if U sub is going to help us, see if we have a situation where we can set it up as a U sub problem. And to me, it looks like we definitely can. It looks like we're going to have some function, natural log of n, and because we also have the derivative of the very same function. So let's set U to be natural log of n. And then, of course, we're going to have the derivative of U with respect to n is 1 over n. And if we multiply both sides by the differential, we get du is equal to 1 over n times dn. And I can tell that it's a really nice substitution to use. I can tell that it helps us out tremendously. I know that just because we have exactly this present alongside natural log of n. We have this entire thing right here, 1 over n dn. So we're going to replace that with du. So this whole thing in this area that I just drew, this is equivalent to just du. So I'm going to rewrite this. I'm going to turn it into, well, first I'm going to add a limit to it. I'm going to make this the limit as alpha approaches infinity, and then we're going to integrate from 1 to alpha. Why did I do that, though? Why did we want to change it into a limit? The reason for that is because it just does not make sense. It just does not make intuitive sense to plug in infinity into a function. So what we're going to do instead is we're going to use a limit to help bridge that gap, because it does not make sense to plug infinity into a function. But what does make sense is thinking about the concept of just picking bigger and bigger and bigger values for alpha. So that's why we need the limit to go from something that doesn't make much sense to go for something that does make sense algebraically. So we replaced infinity with just this limit as alpha approaches infinity. And then we have natural log of n, that's going to be u. We have upstairs in this fraction, it's just a plain old u. And then we have that times du, because du is going to be 1 over n dn. So it turns into something really nice and simple. So if we want to integrate u, we're going to just treat it as if it were any old variable. Yeah, sure, u is a function, and du is the derivative of a function, but the math works exactly the same way. The integration works exactly the same as it would if it were just x dx, a single variable instead of a function. So we're going to just add 1 to this power. We have a u to the first power. We're going to raise that to the second power. We're going to have 1/2 u to the second when we take the antiderivative. And I'm going to be clearing things up as we go. So we're going to have 1/2 u to the second power. So this would be 1/2 natural log of n to the second power. Going from 1 to alpha. So we don't really need the u and the du anymore. We're finished integrating. We're just going to be evaluating the limits as best we can with our endpoints. So we're going to have, we can take out a 1/2. We're going to have natural log of n. So one thing that's important to note is you might be tempted to use one of those natural log rules, or I guess just not natural log specifically, but one of those logarithm rules we know from pre-calc, from algebra 2, that tells us that if we have something like this, it's equal to 2 times natural log of x. So we just take this exponent, move it out to the front, and that's where this part comes from. You want to be very, very careful when you're doing a manipulation like that, because it only applies if the exponent is part of the argument, part of the input of the function. So it does not work in this case because we can see that this 2 applies not only to the n, it just applies to the entire natural log of n. So that's why this logarithm rule does not apply here. You always just want to be careful and make sure that the situation is correct before you decide to do something like that, before you decide if it really applies in the situation. But what we can do is we can move out the 1/2 as a constant multiplier. What we have left is a natural log of n to the second power going from 1 to alpha. And I think I'm going to write that n again. That looks like a travesty. It looks nothing like the letter n. So let's ask ourselves, what happens if we take larger and larger and larger values of n? So we have natural log of n squared. And this will just keep going on and on and on forever. And that's how we know that this diverges, because if we take, let's just forget about the exponent for now. Let's just talk about plain old natural log of n. And we want to take a look at the n behavior. Limit as n approaches infinity of natural log of n. So we can see that a natural log just increases without bound. It doesn't really have conclusive n behavior. It does not converge to a particular value. So that's how we know that, well, if this thing diverges, then this is definitely going to diverge as well. So this would get us infinity. And remember what that means. Remember that whenever we get infinity as our answer to an improper integral, that means that the integral diverges. And we can't, if we can't find the integral, we can't find the sum. We can't find the infinite series either. So the integral tells us, the integral test tells us, tells us that if the integral converges, the series also converges. And it tells us that if the improper integral diverges, the infinite series also diverges. So what that tells us is that now we can conclusively prove for a fact that this infinite series diverges, and thus we cannot find the sum. Let's see how we're doing on time, and then we'll decide if there's anything else we can do for in the rest of this lesson. I think that pretty well covers it. The integral test, I think, is one of the most simple tests for convergence, excuse me. So we don't really need to spend that much time on it. I feel like we should spend more time on the limit concept, on the series concepts, the convergence of series concepts that will be coming after this. So I actually think we are going to have maybe 1 or 2 more lessons on this, just because I want to make sure that we have a really, really good understanding of convergence and divergence of infinite series. So we're going to stop right here, and then the next class we'll be talking about other ways to prove convergence or divergence of an infinite series. All right, well, hope you guys have found this helpful. Have a wonderful evening, and I'll see you in the next lesson. Bye.